Greetings, physics enthusiasts. Welcome to AP Physics 1, Unit 3, Lesson 1. And in Unit 3, we begin to look at rotational motion, things that rotate. And we're going to begin rotational motion by looking at what quantities we should pay attention to, we should measure, and how we would define them. So at the beginning of AP Physics 1, we talked about kinematics. We talked about how something might move. We talked about what that motion meant. Remember, we said motion was change in position relative to a frame of reference. So we're going to look at what rotational motion might be. And then we could talk about how far something moved, and we could talk about how fast that something moved. Similarly, we're going to talk about how much something rotates and how fast it rotates. And then some objects moved at a constant speed, and then other objects moved at a changing speed. And so we're going to look at rotational motion and what it might mean for that rotation to speed up or slow down. So that's what we're going to do in rotational motion as we study it. We're going to look at what's rotating and how we can describe that. So I'm going to make me bigger. And I want to look at this little bitty ruler that I have. It's a very old ruler. It's an engineering ruler, civil engineering ruler. So look that up online. It's got fun little marks on it. But what I did is I put a piece of tape here and I labeled it number 1. And I put a piece of tape here and I labeled it number 2. And all I want to do is say, hey, look at me rotating this. And I'm rotating it counterclockwise because that's the direction we rotate things in mathematics, right? If my fist is the origin, then this is the positive x-axis. And we think about things rotating in mathematics going counterclockwise through the positive, through quadrant 1, and then into quadrant 2, and then down into quadrant 3, and finishing up in quadrant 4, and getting back where we started. So let's just look at this rotating pi over 2 radians. I know you're happy I'm in radians, right? I know you're happy. Okay, so here we are rotating pi over 2 radians. What I want you to do is think about these 2 dots. What about their motion is the same? And what about their motion is different? Ready, go. Stop. What about their motion was the same? Well, they both went pi over 2 radians, or 90 degrees. But what about their motion is different? Was what we're going to call it the angular displacement, what angle they went through, 90 degrees or pi over 2 radians, was the same. But is this distance, this quarter circle, the same distance as this quarter circle? Ooh, no. In fact, this one on the outside traveled farther in the same amount of time. So it probably traveled faster. This one traveled less far. This one doesn't travel very far at all. Right here at the origin, if we make it my ring, it doesn't travel at all. Even though they all rotate 90 degrees or pi over 2 radians, my ring here doesn't travel any distance. And the farther out we go, the more distance they travel. So I would like to talk about, you notice that I was doing an analogy to linear motion. So I'm going to remind you of what we studied in kinematics. In kinematics, we talked about displacement, and we talked about velocity, and we talked about acceleration. And in rotational motion, displacement, velocity, acceleration, we're going to talk about angular displacement. This is velocity. So in rotational motion, we're going to talk about angular velocity. And you can probably guess now, since I'm just putting the word angular in front of these, if this is acceleration, we're going to talk about angular acceleration. So this is displacement. We use the letter X to abbreviate that. Angular displacement, we're going to use the letter theta, the Greek letter theta, to abbreviate that. Velocity, we use the letter V. For angular velocity, we're going to use the Greek letter omega. It looks kind of like a little W. And linear acceleration, we use the letter A. For angular acceleration, we're going to use the Greek letter alpha. So there we go. These are the three letters that we are going to use to describe rotational motion. And now this picture is smaller. But what I'm going to tell you is that for each of these, we went 90 degrees. So the two pieces of tape had the same angular displacement. If I draw a little stick here, if this represents, this green segment represents my ruler. And you can see these two parts, 1 and 2, 1 and 2, 1 and 2, that correspond to my two pieces of tape labeled 1 and 2. You can see that this one didn't go as far, and this one went farther. And how far did they go? Well, those are those arc lengths. So we're going to talk a little bit about arc length. We're going to have to remember some stuff from math class. Don't worry, I'll review it. So the displacement, could be considered this arc length. That's the distance I traveled versus this. So point 1 and point 2 on the meter stick travel different distances, but they have the same angular displacement. If parts 1 and 2 travel different distances in the same time, then this one was traveling faster, this one was traveling slower. Different points on the stick do not have the same linear velocity, but they did have the same angular velocity because they both went the same angle. They both went the same angle in the same amount of time. And then we'll find out that the same thing is true about accelerations. While they may have different A's, linear accelerations, these different points will have the same angular acceleration. So having mentioned that I want to talk about these quantities, maybe we should define them or give them a unit. So angular displacement, this looks like our little angle symbol, and you're used in your math class, you're used to drawing an angle and labeling that angle theta, T-H-E-T-A, theta. But there's two ways of talking about how big an angle is. And I know you learned degrees when you were younger, and then you learned radians, and radians is better. Let's talk about why, and we're going to use radians. So what is the radian? Well, the size of an angle. So we'll start with the positive x-axis, and then we'll go somewhere else, like here. And I want to talk about the size of this angle. Well, do you notice that I have this part of a circle here? This part of a circle. So it's not all of the circle, it's just the part that's intersected here by this angle. There is a relationship between the size of the angle and S, the arc length, this distance, this length, and this radius. And it turns out that it does not matter how big of a circle I draw. I could draw a bigger circle. I don't have another color, but I could draw a bigger dotted circle. And this new arc length, which I'll call S prime, and this new radius, which I'll call R prime, there's the same relationship. S over R, this purple S over this purple R, is going to be equal to this S prime over R prime. And we're going to call that ratio, regardless of the size of the circle, we're going to call that ratio the size of the angle. So another way of drawing that would be, I could draw my circle, and I could draw a small angle like that, or I could draw a bigger angle like that. And so this would be S for my small angle, and this would be S for my big angle. R is the same. So a bigger angle, theta 2, and this is S2, and a smaller angle, theta 1 and S1. Theta 1 is S1 over the radius. Theta 2, bigger angle, is S2 over the radius, same radius. There's just one circle with one radius. So a bigger angle corresponds to a bigger arc length. But it's not dependent on how big of a circle I happened to draw, because S over R and S prime over R prime are the same. So you're like, that doesn't really seem to clear things up. The thing that makes radians better is, what is my unit? Unit for angle measure. And I know you want to say it's degrees. It's not degrees. The unit, well, arc length S is measured in meters. The unit for S is meters. Radius is also measured in meters. So the unit is meters over meters. Meters over meters is no unit at all. There's no unit because the unit at the top and the unit at the bottom cancel out. We call that dimension, D-I-M-E-N-S-I-O-N, dimensionless. It is without dimension or without unit. That makes angle measure really cool. It has no unit, just like coefficient of friction. So there's not really a relationship except that they both have no unit. So it's dimensionless. Pretty cool. Now, I can imagine, look at this angle, this green angle that I drew is just about right. Do you see that this distance, which is the radius, and this distance, which is the arc length, are about the same? So that would be equal to, this angle has a size of 1. Theta equals 1. If I were to draw an angle twice as big, this angle here, this angle here, the arc length is twice the radius. So that angle is 2. And some of you are like, that feels weird to say the angle equals 2. My teacher always said that I should have a unit. The angle is 2 degrees. The distance is 4 kilometers. The time was 55 seconds. You feel like there should be a unit after your number, and that's good that you feel that way. But these things are truly dimensionless. There is no unit. So I could imagine a story where, back when the person discovered the radian, is saying to their students, so this angle has a size of 1. And the kids are like, 1 what? It's got to have a unit. 1 what? And the other person's like, no, this is dimensionless, so it doesn't have a unit. And they're like, but it has to have a unit. So what's the unit? And I can imagine the person being frustrated and running out of patience and making up a nonsense word. Like I would say, okay, fine, it's 1 plat because, I need a unit named after me, right? Or it's 1 Davy. But this person was a little sneakier, and they looked at the picture and they're like, oh, look at that radius, 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 look at that radius. The unit is radian. And they made up the word radian because it looks like a radius. And it's something you can say so people aren't uncomfortable with. The angle size is 1, and no one's going to say 1 what? You can say 1 radian. But when they say 1 radian, they're really just saying it's just 1, but I'm saying radian so that you'll stop asking me what the unit is. Seriously, radian doesn't mean anything. Cross it out. It's a nonsense word somebody made up so you would stop asking what the unit for angle measure is. There is no unit for angle measure. 1. Ta-da! So that's super cool. So sometimes, if radians is in an equation, it'll just disappear. Someone will not write it, and you're like, oh my gosh, they forgot to write radians. No, they just realized that it doesn't exist, so they didn't write it. So angular displacement has a unit, radian, or not. No unit. No unit, dimensionless, or radian are all the same thing. So angular velocity, what is that unit? You can go back and think about that later. I'm going to move on. Angular velocity. Well, velocity is how far you go divided by how long it takes. So angular velocity is how far you turn divided by how long that takes. Well, how far you turn is measured in, so I could say it's in radians per second. Remember that radian really doesn't exist. So the unit for angular velocity is just 1/second. Now, 1/second is fine, but I think it is so much more fun to say s to the -1. S to the -1 is 1/seconds. And who isn't happier when we're talking about a negative exponent, right? That just makes me happy. So the unit for angular velocity is s to the -1, or radians per second, or 1/seconds. Or there's this cisgender dead straight white guy whose name we could use in place of all that. I will let you look that up because we don't care. And then angular acceleration is the rate of change. Regular acceleration is the rate of change of regular velocity. How much the velocity changes divided by how long that takes. So angular acceleration is how much the angular velocity changes divided by how much time that takes. In other words, radians per second squared, or one of my very, very favorite units ever, s to the -2. Yay, negative exponents. So these are our new quantities that we are going to be studying in Unit 3. We're going to be studying angular displacement, angular velocity, angular acceleration. These Greek letters are not units. These Greek letters are abbreviations for the quantities, just like X and V and A are not units. They are abbreviations for the words displacement, velocity, and acceleration. And all of these quantities have appropriate associated units. And then again, we're talking about a thing that's rotating. And what's interesting about things that rotate is that all the different parts of the thing have the same angular displacement as each other. They have the same angular velocity as each other, and they have the same angular acceleration as each other, even though they traverse different distances, and they therefore have different speeds, and they therefore have different accelerations. Okay, so that is that. I talked about those. Very good. Now, there is a phrase that we are going to be using a lot in this chapter, and it is uniform circular motion. So when something is traveling in a circle in a uniform way. So as this ball travels around this circular path, here's the center. If the ball is traveling in uniform circular motion, that means the speed is constant. Now, I'm not saying that everything that travels in a circle has a constant speed, right? If there were a circular track, I know the track, down on the field at school is not a circle, but if there were a circular track, I could run, at 6 miles an hour for a whole hour, and my total distance traveled would be 6 miles. I could travel at that constant speed. But when I started, I was at rest, and then I sped up, and then probably after a few minutes, I slowed down to more of a jog. So me running around the track, I would not be in uniform circular motion because I probably would not have a constant speed. But when I use this phrase, uniform circular motion, to describe something, I am saying that the thing has a constant speed. Uniform circular motion is motion in a circle at constant speed. If we're traveling at constant speed, are we traveling at constant velocity? That's a great question. You should probably pause and think about that. If we are traveling at constant speed in a circle, is the velocity constant? No, it is not. Because if this is V1, a moment later, we've gotten over here, and this is V2. And a moment later, we've gotten over here, and this is V3. If the motion is uniform, one form, right, one, then all of these velocity vectors should be the same length. I didn't do a very good job of that. This one looks too short. But if all of these velocity vectors are the same length, that means the speed is constant. Is the velocity constant? No, because velocity is a vector and it includes both speed and direction. So if these all have the same length, is the speed constant? Yes, but they don't all have the same direction. I'm going this direction, and then I'm going this direction, and then I'm going this direction. So the velocity is not constant. That's going to be very important later on, because acceleration, how did we define that? Rate of change of velocity, not speed. What's the rate of change of speed? 0. It's not fastering, it's not slowing. But the rate of change of velocity, and again, this is for the next video, but I'm going to talk a lot about the rate of change of velocity and how this velocity and this velocity are not the same. They have the same length, so I'm not fastering and I'm not slowing, but they are different vectors. They point in different directions. And if they point in different directions, this direction and then this direction, then that velocity has changed. And if the velocity has changed, then we are accelerating. We'll talk about that at length in the next video. But now it's time to move on. In uniform circular motion, speed is constant, velocity changes. Big deal. Make sure you write that down and continue to think about it so that it gets gets sunk in so that you really remember it. All right, there's a couple of adjectives that we use when talking about circular motion and circles. Sometimes things point toward the center of the circle. For example, if this were some kind of planet going in a circle around a star, or if it were some moon going in a circle around a planet, this arrow might represent the gravitational force that the sun exerts on the planet. So this direction matters. And this direction has a name, centripetal. Centripetal. I have heard people smarter than me say centripetal. So say whatever you want. I say centripetal though. Centripetal is an adjective that means toward the center. Centripetal has an antonym. An antonym means meaning the opposite. So there is a word that means away from the center. And that word is centrifugal or centrifugal. Now, it just so happens that everything we talk about in this unit that has a direction toward or away from the center, the answer is always going to be toward the center. We are going to use this adjective lots. We're going to talk about things that point toward the center. You know what we're not going to talk about? We're just not going to talk about anything that points away from the center. So this way, toward the center, centripetal. That's going to be useful this chapter. This direction, away from the center, there's a word for that, it's centrifugal. It just so happens that that direction is not going to be part of our discussion. So if you want, since there's an F in there, you can say this is the F word in physics, and we just don't need it. We just don't need it. So if you find yourself talking about pointing away from the center or needing the use of this adjective, you're probably missing something, and go back to talking about this one. We're just going to talk about a lot of stuff that points toward the center, me, and not stuff that points away from the center. So that's a little hint for this chapter. All right, I have two little sets of equations to show you. Oh my goodness gracious, there's my piece of paper. That's the wrong piece of paper. Let's pause for a second while I grab my piece of paper. And I'm back. Okay, two sets of equations that we're going to use lots and lots and lots this chapter. Go back to my ruler that's rotating. So when we have something like that, that rotates, you know, from here to here to here, there is a relationship between how far it's traveled, and I'm not talking about displacement, which would be this chord on the circle. I'm talking about this distance traveled, which would be the arc length. So arc length S over radius R, this is the arc length, then this is my angle theta. So remember, theta equals S over R. I'm hoping you remember that from math class. If you do remember that from math class, then you can get S arc length. Let's write X instead. And S or X equals R times theta. So there is a relationship, a mathematical relationship between the linear distance traveled and the angular quantity, angular displacement. So what I'm going to do is I'm going to try to get a relationship between these two, which I just did, and then a relationship between these two, and then a relationship between these two. X and theta, how are they related? V and omega, how are they related? A and alpha, how are they related? Well, if I were to divide both sides by t, what is x over t? Distance over time, that's velocity. I'm going to keep r. What is theta over t? The angular displacement divided by the time that took, that's angular velocity. Oh, and what if I divide both sides of this by t? Velocity or change in velocity divided by time is acceleration. Keep the r, divide by t. Omega, change in angular velocity divided by the time that takes is alpha. So I love to put all three of these equations together. X equals r theta, V equals r omega, A equals r alpha. And it helps us if we understand the linear quantities, how they are related to the angular quantities. And it helps me see that the ones with the bigger radius, this has twice as big of a radius of motion as this one. Therefore, this one goes twice as far and travels twice as fast as this one. And if they do not have a constant speed, if I start slow and go faster, slower, faster, the angular acceleration is related to the linear acceleration in the same way. Sometimes people get all these equations right, except they put r on the wrong side. So either start with what you should know from your math class and translate it into this, and then just make the next two. Or look at the units. What's the unit for theta? No unit. What's the unit for radius? Meters. What's the unit for x? Meters. Does meters equal meters times no unit? Yes, it does. That works. If I had written it the wrong way, I'm very briefly going to write it the wrong way. If I'd written x times r equals theta, this is wrong. Instead of r being on the right, I put r on the left. This is wrong. What would have happened? I would have had meters times meters is no unit. Does meters times meters equal no unit? No, meters times meters is meters squared. That's wrong. Bad. Scribble it out. No. So anyway, you can either figure these out or just guess and see if the unit works out. So that's one set of helpful equations. Helpful equations. Another set of helpful equations, and this is the last thing I'm going to say is, the set of helpful equations is the kinematic equations. Remember that 2 of our kinematic equations started with x and 2 started with v final. And I'm just writing them really quickly here. And they should look very familiar because we used them a lot in the previous units, in each of the previous units. These equations translate letter for letter into the rotational world. We just have to remember that we're always going to replace x with theta, we're going to replace v with omega, and we're going to replace a with alpha, letter for letter. So x becomes theta, v becomes omega, so v naught becomes omega naught, t does not change. Constants like 1/2 do not change, a becomes alpha. Theta is omega naught t plus 1/2 alpha t squared. In other words, the total angle traveled is equal to the original angular velocity times the time of motion plus 1/2 times the angular acceleration times the time squared. Translation, letter for letter. So you should be able to do these on your own, but I'll just write them really quick and let you practice using them this chapter. There they are. So these are the 4 kinematic equations for linear motion. These are the 4 kinematic equations for rotational motion. Also helpful. And that's our introduction to Unit 3 in AP Physics 1, rotational motion. Lots to see here. Feel free to watch again. I'll see you soon in class.